have covered the basics on kind of like the derivation of the dimensional or the dimensionless forms of equations of change for non-isothermal systems. Now let's take a look at how we can use the idea of dimensional analysis to analyze like real-world problems. The example we're presenting here is looking at free convection in a horizontal fluid layer, looking at the formation of Bernard cells. So let's first, draw a schematic on the problem statement that we're looking at. Okay, so let's say we have a fluid, a layer of fluid. Maybe we can just use a marker. So we have a fluid layer that's kind of, sandwiched between two parallel plates. So we have an upper plate and a lower plate. Okay, and then on the side of this, thin film layer of fluid, we have insulating materials. Okay, and the upper plate is constantly held at, let's say, T equals to T1, and the lower plate held at T equals to T naught. Let's define the coordinates. So assuming this would be a, like a circular plate, so we have the axial direction in Z. We have a radial direction, that's R. Let's define the lower plate as Z equals to 0, and the upper plate and Z equals to H. Z equals to H. Okay. And the side here is insulation. Insulation. Okay, so this would be a side view of our system. Side view. Okay, and we'll come back to the top view later on. But so now the question is, you have a layer of fluid that's sandwiched between two parallel plates. Okay, and so if T1 equals to T2, so let's say if, T naught equals to T1, then that means there's no temperature gradient. And that means the fluid layer is stagnant. But what if T naught is greater than T1? T naught is greater than T1. Just by thinking about the problem, if T naught is greater than T1, that means there's a possibility that the fluid at or close to the bottom plate has lower density, because the density of fluid would be a function of temperature, right? Usually, as the temperature gets higher, the density gets lower. If the density gets lower, then you might have a buoyant force. That's, you might have buoyant force that's going to cause free convection. Okay, so we want to analyze this type of systems. So basically, it's a problem about analyzing how temperature gradient affects your density gradient. And that would cause instability of the system. Also, it's an analysis looking at the competition between buoyant force and viscous drag. So basically, our objective here is to determine, using dimensional analysis, to look at the dependence of fluid motion under a condition with temperature gradient. Okay? So let's put that into words. What we're trying to do here is to determine the functional dependence of this fluid motion and the conditions under which it may be expected to arise. Okay? So again, the question is rather simple, is that if you have a thin layer of fluid or a stagnant layer of fluid, if the bottom and the top plate has the same temperature, there would be no temperature gradient. The fluid layer would remain stagnant. But what if the bottom plate has a higher temperature than the upper plate? Then you can expect that the fluid closer to the bottom plate would have a lower density, because the density is a function of temperature. And if that difference in density gets large enough, it may overcome the viscous drag force of the fluid, and then free convection might start happening. What we're trying to do here is to use dimensional analysis to analyze this problem to see under what kind of condition you would start expecting free convection, and under what kind of condition free convection may not occur. So coming back to our equation of changes, let's look at the equation of changes in the dimensionless form. So what we're going to do now is we want to first describe the system, by dimensionless equations of change. So the first one would be the equation of continuity. We have the dimensionless gradient operator dot product with dimensionless velocity equals to 0. Okay, and then we have the equation of motion. We have the substantial derivative of the dimensionless velocity equals to the dimensionless gradient of the dimensionless pressure plus mu times we should actually have let me try to not skip ahead of myself. So the equation of continuity, let's start from the non-dimensionless form. So the usual form first. So the usual form tells us it's going to be mu Laplacian of velocity minus rho g beta times T minus T bar. And then we have the equation of energy. Which is rho Cp dt dt equals to thermal conductivity times the Laplacian of temperature plus mu times the stress tensor. Okay, but remember, for free convection, viscous dissipation is kind of be negligible. So negligible. So we're just going to take that out real quick. So remember, for free convection, when we are trying to, the key here is to determine the characteristic velocity. Remember that for free convection, and if it's not a creeping flow problem, we would choose the kinematic viscosity over L naught, or alpha over L naught as our characteristic velocity. And for this particular problem, we can view it as a creeping flow problem. So the dimensionless forms becomes the following. Becomes equation of continuity gives us the dimensionless gradient of the dimensionless velocity equals to 0. The equation of motion becomes dv dt equals to the negative gradient of p plus the Prandtl number times the dimensionless Laplacian of the dimensionless velocity minus the Grashof number, Prandtl number square times the dimensionless temperature minus 1 over 2. And then you have the equation of energy saying that it's going to be the substantial derivative of the dimensionless temperature equals to the dimensionless Laplacian of the dimensionless temperature. Okay, and now let's look at the boundary conditions. So boundary conditions. We have what we have at z equals to 0. We have no slip condition, v equals to 0. T equals to T naught. At z equals to h, we have no slip condition, T equals to T1. And at r equals to r, again we have no slip condition. And we have an insulating wall, so there's going to be no heat flux at the boundary. So the partial derivative of temperature with respect to radius is going to be 0. Again, we want to transform the boundary conditions into dimensionless forms. So again, let's do that. So dimensionless form. We now have at the dimensionless z equals to 0, so that's z over h. We have the dimensionless velocity as 0. We have the dimensionless temperature equals to 0. At z equals to 1, we have again dimensionless velocity as 0. Dimensionless temperature equals to 1. And at r equals to r over h, we again have zero velocity and the gradient also being equal to 0. Okay. Now, what if the plate or the radius is substantially larger than the thickness of the fluid layer? Then we can, view it as an infinite large plate, and the problem becomes just one-dimensional. Okay, so let's do that simplification. Let's assume, the radius of the fluid layer is much greater than the thickness of the fluid layer. Then the system behavior is now solely dependent on the Grashof number and the Prandtl number. Right, so again, let's go back to our dimensionless equation of change right here, dimensionless form. If you look at the fluid motion now, everything is only now dependent on the Prandtl number and the Grashof number, right? Everything else is now dimensionless, and these number, the Grashof and Prandtl number, will determine the contribution of different terms here. Okay? So, some notes here. So the first note is, if the fluid is a steady creeping flow, so that means that for creeping flow, that means inertial forces can be neglected. Inertial terms going to be negligible if the Reynolds number is much smaller than 1. Okay, and if that's the case, that means the substantial derivative term here is going to be 0. Why is that? Because the substantial derivative is actually going to be partial v partial t. That's going to be 0 for steady flow, and the gradient part would be v gradient v, right? And if it's a creeping flow, that means inertial terms are negligible. So steady flow means it's steady state, so the time-dependent term is 0. Creeping flow means that the inertial terms are negligible. Okay. So that means the whole left-hand side of the equation of motion can be set to 0. Right, so let's click mark here. The second note is we would like to define another pressure term that's another dimensionless pressure. Let's use a larger capital P, and let's say, and using this type of cap equals to the Prandtl number times the original dimensionless pressure. Then the equation can be further simplified. So we have the left-hand side being set to 0, and the right-hand side being just the capital P minus the dimensionless Laplacian of the velocity, and minus the Grashof number, Prandtl number, times t minus 1 over 2. Okay, so what we're doing here is basically just transforming. So the left-hand side, if it's a steady creeping flow, the left-hand side is going to be 0. And now we're going to also divide the whole equation by the Prandtl number. Okay, so we're going to divide everything by the Prandtl number. Sorry. The Prandtl number. So Prandtl disappear, square disappears. And we're just defining a new pressure term. Okay. So you see that now the whole equation is solely dependent on one dimensionless group or one dimensionless coefficient, right? And in this case, sorry, I should also put missing a gradient here. Now, so you can see that this very special number, which is the product of the Grashof number and the Prandtl number, it is actually now we define this as a new dimensionless number called the Rayleigh number. So the Rayleigh number, which equals to the product of the Grashof number times the Prandtl number. And this equals to what? Equals to rho square G beta times T1 minus T naught over, there's also the height cube Cp over mu, the viscosity, and the thermal conductivity of the fluid. Okay? So finally, let me just correct this, and maybe this is not even needed. We'll just say divide all by Prandtl number. Makes it easier to understand. Okay, so now our equation becomes the following. We can move the viscous term to the left-hand side, and all the rest staying on the right-hand side. So we have now the dimensionless Laplacian of velocity equals to the pressure term over the Prandtl number minus the Rayleigh term times T minus 1 over 2. Okay, so if you have typically for free convection problems, you do not have a pressure gradient driving the fluid flow, right? You might have some so basically the first term here actually is going to contribute very less. So that doesn't really contribute. In some cases, we can even just neglect this term, right? So we can just neglect it. Okay, so basically the whole equation suggests that the Rayleigh number is the critical factor that's determined whether fluid flow is going to occur. So the final equation suggests there may be a critical Rayleigh number, Ra, when exceeded fluid motion will occur. So what does that mean? So if we erase this part, you can see that the velocity distribution, the velocity distribution would be depending on the Rayleigh number. If the Rayleigh number is very small, so if the Rayleigh number is very, very small, then may be set to 0. Then there will be no fluid motion, right? Because if you integrate the left-hand side twice with the boundary conditions, there's going to be no fluid motion. Okay? But if Rayleigh number is sufficiently large, then it might drive fluid motion. So experimentally, the critical Rayleigh number, a critical Rayleigh number around 1700 plus minus 51 for R over H is much greater than 1. If the Rayleigh number is smaller than the critical Rayleigh number, fluid is stationary. And that means your heat flux just follows the conduction. So the heat flux in the z direction is just going to be transported by pure conduction. So that's going to be the thermal conductivity times the temperature gradient, T0 minus T1 over the fluid thickness. But if the Rayleigh number is larger than the critical Rayleigh number, then the heat flux rises sharply. Okay, and some other notes is that the assumption of creeping flow is, so the assumption of creeping flow is reasonable when Prandtl number is very large. So remember that the Prandtl number is defined as what? It's defined as the ratio between momentum transport and energy transport by molecular mechanism. So if the Prandtl number is very, very large, that means that the momentum transport by viscous or molecular mechanism is much faster or greater than energy transport. Okay? And then other notes. So if per plate replaced by a liquid gas interface, the critical Rayleigh number is around 1100. And the last but also very important point is that instead of the temperature gradients, surface tension gradients might also drive free convection. So surface tension gradients may also drive or result in free convection. And is easily messed up with temperature gradients. Okay, this is for, application-driven part is if someday you are, designing or using this type of process. Let's say you have a fluid layer that's stagnant and you want to prevent, free convection from happening, but you still need a temperature gradient nevertheless. Sometimes it is the surface tension gradient that's causing your free convection, not the temperature gradient. So maybe you might figure that, why am I still having a free convection even though my Rayleigh number is, way below the critical Rayleigh number? In such a situation, then you want to think about surface tension gradients instead of temperature gradients. Okay? So let's quickly review this example. And this is just a simple example showing how we can use dimensionless forms of equation of changes to analyze problems. And the problem here is very simple, is for a stagnant liquid layer, if you have temperature gradient inside that, across that layer, will you have free convection or not? And by using the dimensional analysis technique, we have come to the following, right? So after doing the dimensionless analysis for free convection, in this case, I think we choose alpha over L naught as our characteristic velocity. So then we get to the bottom three dimensionless form of equation of change. Okay? And then we also made an assumption that if you have a steady creeping flow, then the left-hand side of the equation of motion can be set to 0. And pressure term or pressure gradient is typically negligible for this type of systems. So you end up actually having a result that the temperature distribution is solely dependent on what? It's solely dependent on the product between the Grashof number and the Prandtl number, which is the Rayleigh number. Okay? And what is the Rayleigh number? Let's take a look at that too, right? So remember the definition for Grashof and the Prandtl number. So the Grashof number is basically the ratio between what? The Grashof number is the ratio between buoyant force and inertial force. And the Prandtl number is momentum transport by viscous, so kinematic viscosity over thermal conductivity, right? So what this tells us is that the Rayleigh number is basically describing, the conditions here. So for large Grashof number, that means the buoyant force dominates inertial force, free convection will occur. But also you need to consider the second thing is the relative ratio or the relative portion of viscous momentum transport and energy transport by conduction. And why is that the case? Because if you look at our Rayleigh number again here, if the Rayleigh number is very large, that means what? That means you have very small inertial forces, and that's typically the case for free convection. There's no inertial force at all, basically. And if you look at the Prandtl number, you can see what's happening here is if the Prandtl number is very large, that means that thermal conduction is actually not transport as fast as the momentum transport by viscous drag. Okay, that means what? That means that you will still maintain a large enough temperature gradient to cause that difference in density, which causes fluid motion. But what if you have a very small Prandtl number? That means you have a very fast conducting fluid medium. Then the temperature transport or energy transport so fast that you may not have a large enough temperature gradient to cause that density gradient to cause free convection. Okay, so that's kind of like the physical meanings behind the Rayleigh number. Okay, and if you look at the definition of the Rayleigh number here, you can also see what's happening is that if you just look at the fluid property here, the fluid property includes the viscosity and thermal conductivity, right? So basically, a less viscous and a less thermal conductive fluid will give you a higher Rayleigh number. Let's see if this is correct. I'm thinking something's wrong here. Oh yeah, that's correct. So if basically what happens here is that if your viscous drag is large, then fluid motion doesn't occur as easily. If thermal conductivity is fast, then temperature distribution is not going to be that great. But if the thermal conductivity is small, that means you will have a large temperature gradient. So a more viscous and a more conductive fluid results in a more stable fluid that doesn't give you a free convection. Okay, hopefully I'm making this summary clear enough for you to understand. Sometimes I get a little bit confused by my wording too. So let's again come to our Rayleigh number here. So again, the fluid property here is determined by what? The fluid property here is the viscosity and the thermal conductivity. If the fluid is more viscous, that means it has a large drag force, so it's harder to move. The molecules in the fluids are harder to move, so harder for fluid motion, harder for free convection. Okay, so larger viscosity gives you lower Rayleigh number. That makes sense. The thermal conductivity. If you have a higher thermal conductivity, that means the temperature gradient evens off faster. Okay, so that means you won't have such a large of a temperature gradient to cause the density difference. Okay, so that also makes sense. So a very viscous fluid with a fast conduction or high thermal conductivity is not going to favor free convection to happen and will be more stable. Okay, so I think we will call that a end for this example. And next time we will come back with another example that's also very interesting, looking at fog formation during dehumidification process.